Today we're going to discuss how to balance redox reactions in acid solution, which is going to differ from the way we balance redox in base. So we're going to do acid first, and just like when we did all our other stuff involving acids and bases, if you understand the acid version, then the base version is just a tiny little modification of the acid version. So that's why we're looking at the acid version first, just like we did Ka before we did Kb. Now, there was an assignment that I gave you yesterday. I said as your pre-assignment for class today, you need to review your rules for assigning oxidation numbers, because that's something that's covered very extensively in Chem 1. We're not going to spend class time today going over it. So make sure you've refreshed your memory on the rules for assigning oxidation numbers. This is the handout that I gave you in class last time. And also it's posted on the course website. So if you need to review, there's where you can do that. Also, if you download the notes that we're going through right here, these links, that's the lecture that we did last semester on redox. That's the intro chem version on redox. Guess what? It's the same. And then here are some short videos if you don't want to sit through a big long lecture, 1 or 2 minute videos. Again, refresh your memory if you don't remember how to assign oxidation numbers and how to identify redox reactions. It's on you to go review this, okay? Because we spent a full week on this in Chem 1. So what we're going to be doing today is we know how to balance equations, right? That's something we learned in Chem 1. We balanced it in terms of atoms, right? You know, number of carbons on the left needs to match the number of carbons on the right. However, electrons get transferred in a redox reaction, and we have to balance that as well, okay? You have to have the correct number of electrons, showing that the law of conservation of mass is satisfied, even with the electrons, that none of those electrons are ever lost. They're not destroyed, they're not gained. And so we're going to use what's called the half-reaction method. So here's how we do this. And again, we're looking at it in acidic solution, but when we deal with basic solution works just like acid. There's just a tiny little modification. So the first thing we have to do is we've got to go through and figure out who gets oxidized and who gets reduced. And then we're going to write half reactions. We're going to write a half reaction for the oxidation, and we're going to write a half reaction for the reduction. It'll make a lot more sense when I just show you examples. And by the way, if you don't want to write all this down, it is in the notes that are online already. Then we're going to balance each half reaction. I mean, that's the main bulk of what we're doing today. We're going to balance for stoichiometry. We're going to balance for a number of electrons that get transferred. And then these parts are only going to apply to us if hydrogen and oxygen are involved. So we're going to balance everything other than hydrogen and oxygen first. So I guess I should shorten that a little bit. We're going to balance oxygen using H2O, balance hydrogen using H+. And then if we need to, we can balance charge. But you're probably not going to if you do this part correctly. Then we're going to multiply the half reactions by an integer so that they cancel. Again, this will make a lot more sense when you see it. Add them up, and then double check our arithmetic. So let's do a really easy one first. These examples that we're doing first do not involve hydrogen. They don't involve oxygen. Okay, so these are the super simple ones, right? They're neutral. So if this is the net ionic equation and I say, all right, balance this for me. First thing you got to do is you've got to go through and assign all your oxidation numbers. Copper is a pure element in its most stable form. That's why it's 0. Monatomic ion, oxidation number is its charge. Pure element in its most stable form, monatomic ion. So we compare before to after. Copper goes from 0 to +2. That means that it is oxidized, right? It's losing electrons. This is what we learned in Chem 1. And then silver's gaining electrons. It goes from +1 to 0. It's reduced. Now in Chem 1, that's where we stopped, right? We just left it right here and we walked away. But this is actually an unbalanced equation. So now let's actually balance this, because right now if you look at this, you're like, oh, copper, there's 1 and 1, there's 1 and 1, but it's not balanced in terms of number of electrons. So in Chem 1, we just looked at it and said who's oxidized, who's reduced, but now we're actually going to balance it in terms of number of electrons. So we're going to write a half reaction. And I just picked the oxidation first because I listed it first. So what happened? Copper went from 0 to +2, right? So if you go from an oxidation state of 0 to +2, that means you lost 2 electrons. And if you're being oxidized, that means you're writing electrons as a product, right? Oxidation is loss. If you remember the oil rig, or if you're using the Leo, says Gur, right? Lose electrons equals oxidized. So if you are being oxidized, you're writing electrons as products. Does everyone see why this +2e is here? Do you understand where this is coming from? And why it's 2 and not 1? Right? Oxidation number of copper initially was 0. It became +2. How do you get from 0 to +2? You lose 2 electrons. Everyone with me here? Now let's do the reduction. Reduction is gain, if you like oil rig, or gain electrons equals reduced, right? So what happened here? Silver was at +1, and it became 0. How do you get from +1 down to 0? You gain 1 electron. So in a reduction, you write electrons as reactants. In an oxidation, you write electrons as products. Does everybody understand this half reaction? You write a half reaction for the oxidation, you write a half reaction for the reduction. They are 2 separate processes. We're going to look at them separately. They are occurring at the same time, but they're 2 separate processes. Does everybody see how this came to be? Does this make sense? All right, now what we want is we want the electrons to cancel out. When I add these up, I want the electrons to cancel. Because if I have 2 electrons on the products and 2 electrons on the reactants, when I add them up, they'll cancel. Well, this is 1 electron, this is 2. So if I multiply this whole reaction, the whole reduction half reaction by 2, including the Ag plus and the Ag, if I multiply everybody by 2, the 2 electrons cancel. And then when I add them up, Cu plus 2 Ag plus produces 2 Ag plus Cu2 plus. Does it make a difference if you wrote the order here reversed? Would that make a difference? Cu2 plus 2 Ag. Is 1 plus 3 different from 3 plus 1? No. Okay, so the order does not matter. So long as you have the correct substances on the products and the correct substances on the reactants. And now we want to check our work. How do we check our work? We want to make sure it's still balanced in terms of number of atoms. 2 Ag, 2 Ag. Okay. 1 Cu, 1 Cu. Good deal. We also want to make sure the charge is the same on both sides. This side has a net charge of +2, right? Because 2 times +1. This side has a net charge of +2, because you've got 1 plus 2. So it's balanced in terms of charge, net charge of +2, net charge of +2, and it's balanced in terms of stoichiometry. Having this 2 here doesn't hurt anything, right? 2 Ags is still 2 Ags. And that's our final balanced equation. Now again, this is a simple one. This is a neutral one. In other words, we're not dealing with the acid component yet. We're looking at some baby ones before we get into the more challenging ones. Does everyone understand how this one worked? You ready to try one for yourself? Ready to try one? Okay, here's the net ionic equation. Again, this is a real simple one. We're going to crawl before we run. Here's the net ionic equation. Cobalt-3 and nickel metal producing cobalt-2 and nickel-2. So take a second and balance this one. I'll pause the recording. Let's go over this and see what we came up with. So again, these are the easy ones. Notice there's no hydrogen involved. There's no oxygen involved. So we're just looking at some really, really simple ones. We want to make sure we understand the really easy ones before we get into the more involved ones. So this is the net ionic equation. We need to first give everybody oxidation numbers and figure out who got oxidized and who got reduced. Monatomic ion, so oxidation number is its charge. Pure element is most stable form. Monatomic ion, right? So cobalt-3 becomes cobalt-2, so that's a gain of electrons, that's a reduction. nickel metal becomes nickel 2 ion. That's a loss of electrons, right? So CO3 plus is where we're going to begin for the reduction half reaction, and the nickel is where we're going to begin for the oxidation half reaction. Do we agree so far? All right, let's do the oxidation half reaction. If you're being oxidized, that means that electrons are a product, right? Oxidation is loss, or lose electrons equals oxidized, whichever mnemonic you want to go with. If you go from 0 to +2, that means you've lost 2 electrons. For the reduction, remember reduction is gain, or gain electrons equals reduction, whichever method you prefer. To go from +3 to +2, that means you must have gained 1 electron, right? So reduction means you're writing an electron as a reactant, and oxidation means you're writing an electron as a product. Do we agree on the 2 half reactions? Is everybody with me on the 2 half reactions? So now all we need to do is set it up so that my electrons cancel when I add. We've got 2 in the oxidation, we've got 1 in the reduction. So if I just multiply the reduction half reaction by 2, when I add them up, the 2 electrons cancel, right? 2 electrons on the reactant side, 2 electrons on the product side. Now let's check that we haven't messed anything up in terms of our stoichiometry. 2 cobalts, no big deal. 1 nickel, no big deal. Let's check in terms of charge. We should have a net charge that's the same on both sides, right? 2 times 3 is +6. And then we've got 2 times 2 is 4, plus 2 is 6. So a net charge of +6, a net charge of +6. So it's balanced in terms of law of conservation of mass, in terms of the atoms, and it's balanced in terms of charge. So we can conclude that this is a balanced redox reaction. Do we understand how we did this one? If you made a mistake, do you see where you made it? Most mistakes are made in identifying oxidation numbers. All right, try one more. This is another easy one. Magnesium metal is in combination with aluminum ion, giving us aluminum metal and magnesium 2 ion. That's the Net Ionic Equation. So we've removed all the spectators, made it nice and easy. So I'm going to pause the recording and give you a chance to try this one. All right, let's see what we did here. So again, the first thing we need to do is identify who's oxidized and who's reduced. So magnesium is 0, aluminum ions +3, aluminum metal is 0, magnesium ions +2. So the magnesium is where we're going to begin for the oxidation half reaction, and the aluminum ion is where we're going to begin for the reduction half reaction. Do we agree? Do we agree? All right, so let's write our oxidation half reaction. Magnesium starts as 0 and ends as +2, so that means that it lost 2 electrons. And aluminum ion begins as +3 and ends as aluminum metal, so it goes from +3 to 0, which means it gained 3 electrons. Can I turn a 3 into a 2 or a 2 into a 3 by a simple multiplication? No, but I can turn them both into the least common multiple, right, which is 6. So if I multiply the oxidation half reaction by 3 and the reduction half reaction by 2, that becomes a 6, that becomes a 6, which makes them cancel. So when I add, I want to make sure that I haven't messed anything up. 3 magnesium, 2 aluminum, 2 aluminum. We also want to make sure I'm still balanced for charge. 2 times +3 is +6 on the reactant side. 3 times +2 is +6 on the product side. So I'm balanced in terms of atoms, and I'm balanced in terms of charge, so I am good. Now again, if you wrote the 2Al3 plus 3Mg, would that have made a difference? The order here doesn't matter, right? So long as you've got the correct substances on the reactants, the correct substances on the products, the order that you put them in makes no difference. How do we feel on these real easy ones?
Pretty good.
Pretty good? All right. So let's get into some ones that are going to make us think a little bit more. Now here's the theory. Here's the theory behind what we're doing. This is occurring in an acid. Okay? So because it's occurring in an acid solution, that means that water's the solvent, right? So that means I can yank as many waters as I want out of the solvent and put them as part of my reaction if I want to. There's no limit on the amount of H2O available to me. Likewise, there's no limit on the amount of H+ that's available to me. So that's how we're able to do this. Okay, because this is occurring in an acid solution, acid is the solvent, so that means I can yank as many of these out of the solvent and write them as part of my reaction as I want. And I can yank as many of these H2Os out of the solvent as I want and write them as part of the reaction. Okay? So we're going to be adding H+, we're going to be adding H2O. I don't want you to think that we're violating the law of conservation of mass here, because we're not. Because this is occurring in an acid solution, that's how we can add H2O to our reaction, or add H+. Because prior to this point, I've always told you, you can never, ever, ever just add something for the sake of adding, right? But because that's our solvent, we can yank H2Os or H+ from the solvent and put them in our reaction, and we're not violating the law of conservation of mass by doing that. Do you understand the theory? Okay, this is occurring in an acid. Does the theory make sense of what we're going to do? All right, it sounds really wordy, but I think once you see examples, it'll make sense. So let's start with this one. Now, this is not the net ionic equation, right? In the past, so far, we've seen all net ionic equations. But let's go through one where it's not the net ionic equation. I want to give you the whole shebang. So here's the molecular equation. First thing we got to do is the same thing that we did in the past. We're going to assign everybody an oxidation number. +1, -1, 0, +1, +5, -2, +4, -1, +4, -2, and +1. If doing this part is challenging for you, you need to go back and review the Chem 1 handout, okay? Go watch the videos from Chem 1 on how to assign oxidation numbers if this is something that's going to give you a lot of headache, okay? Because we spent a long time in Chem 1 assigning oxidation numbers. So the first thing we do is we assign all our oxidation numbers. And we're going to ignore some of the things that, like for instance, what did I drop? I dropped sodium, right? That's +1 and +1. Cleaned it up a little bit. So we've got -1, 0, +5, -2, +4, -1, +4, -2. So what's going on? Tin is going from 0 to +4, right? Because nitrogen stayed, and then, excuse me, nitrogen is going from +5 to +4. Oxygen isn't changing, chlorine's not changing, right? So tin, 0 to +4, and nitrogen, +5 to +4. So tin loses electrons, that's why it's oxidized. Nitrogen's gaining electrons, that's why it's reduced. So we're still going to break this up into half reactions, but now our half reactions are a lot more complicated, right? Now, here's the fun part. If I want to do something involving tin as a half reaction, I got to include the whole thing that tin is a part of. Okay? I can't just say tin going to tin and just ignore the rest of this complex ion. I can't do that. Right? Tin is a part of this complex ion. So when I write my half reaction, I got to write it as tin going to this complex ion. And then how many electrons got lost? It went from 0 to +4, so that's why there's 4 electrons written here. Okay? Now, go back and look at the problem. Chloride is written as one of my reactants. Right? Chloride is part of my reactants. It's actually HCl, which is a strong acid. Right? So I've got HCl floating around in my solution here. I got to balance this thing for stoichiometry, and I got to balance it for electrons. So far, is this a balanced, excuse me, half reaction? It's not, right? Because you look at this and go, I got chlorine as a product that wasn't there as reactant. So what can I do? Well, again, chloride's floating around in my solution already. It's floating around in the form of HCl specifically. So I can grab some of that out of the solid, out of the spectator ions and dump it in here. Okay? So that's where this comes from. I'm not violating the law of conservation of mass. Because HCl is my spectator ion, essentially, right? I can pull chloride out of that and write it as part of my half reaction. Got to balance it for a number of atoms as well as electrons. It went from 0 to +4, so that's why there's 4 electrons here. This 6Cl minus is because there are 6 Cls, and HCl is part of my solution. Now let's do the reduction half reaction. Okay, first thing we got to do is we look at, okay, nitrogen went from +5 to +4. So that's a gain of 1 electron. Woohoo! But what's the problem now? I've got 3 oxygens on this side and 2 oxygens on this side. When oxygen and hydrogen come into the picture, this is where we start to have to use the H2Os and the H pluses that are part of my solvent. So I've got 3 oxygens on this side and only 2 on this side. So I need another oxygen on this side to make it balanced, right? So I balance oxygen by adding H2O. H2O is my solvent. I can add as much as I want, right? So if I need to get the total number of oxygens up to 3, I just write H2O, right? 3 and 2 plus 1 gives me 3. And there are 3 on this side as well. Does everyone see why we wrote plus H2O here? To balance the oxygens. I need 3 oxygens on the product side. I've got 3 on the reactant side. I only had 2 to work with. Water's my solvent, so I can yank as many H2Os out of the solvent and dump it into my equation, and I'm not violating any rules by doing that. But now I've created a new problem, which is what? I don't have any hydrogens on the other side. So I balance hydrogen using H+. Because again, this is occurring in acidic solution. This is part of the acid. If I have 2 hydrogens in H2O, to offset that, I would just put 2H+. Again, we're just grabbing this out of the solvent, dumping it in, and the subscript here should be AQ. That's just me being lazy. All right, you need to have that subscript for state of matter. There we go. Okay, so we balance oxygens using H2O, and then that's going to create a problem with having too much or too little hydrogen. So we'll put H+ to make it so that we've got 2H, 2H, 3O, 3O, 1N, 1N, and then that 1 electron comes from the fact that this was +5 and now it's +4. Now I've got a balanced half reaction. So everyone see how we did this one? Things get a little messier when oxygen and hydrogen enter the party, right? But do we understand why we did the things we did and how we're able to do it? Part of the solvent, so I can put as many here. I could put a coefficient of 5 million there if I wanted to. I wouldn't need to, but I could, right? Because that's just the solvent. Same thing here. I can make this coefficient any number I want because it's the solvent. So now we're just going to add them up. There are 4 electrons in the oxidation. There's only 1 electron in the reduction. So I'm going to multiply the entire reduction half reaction by 4. Right? So I got to carry that 4 to here, and here, and here, and here, and here. Right? And now when I add these up, I had to go onto a second line. So if that happens to you, that's okay. If you're writing and you run out of space, just make sure I can follow it. 6Cl minus plus Sn solid plus 8H plus, that's the whole reactant, oh, plus 4NO3 minus. They're all my reactants. Produces the complex ion plus 4NO2 plus 4H2O. And that's my final balanced redox reaction. A lot messier, a lot more writing, but in terms of the method, I don't think it's going to make things too difficult. You understand why you're adding H plus and you understand why you're adding H2O. Any questions on this one before you try one for yourself? Questions? Ready to try one? All right, so what, just for review, what ion is that? It's what? Permanganate, what's that? Oxalate. All right, so here's a net ionic equation. I was being nice. Here's a net ionic equation. Balance it. I know it says example, but you can do it. Balance it. I want you to balance that. See if you can figure it out. Because there is a nice little trap laying there in wait. So see if you can find the trap. Okay, let's see how far you made it. Because there is a little sneaky snake kind of thing to think about in this one. So the first thing we have to do is we've got to assign our oxidation numbers. Oxygen isn't changing. It's -2, -2, -2. So it's not changing. We don't care about it in terms of is it participating in the redox? And the answer is no. Right? Manganese goes from +7 to +2. So that's a big time reduction, right? And carbon goes from +3 to +4. So that's the oxidation, right? Manganese gets reduced. That's where we'll start our reduction half reaction. Carbon is oxidized. So we'll start our oxidation. Now remember, can I divorce the carbon from the oxygens when I'm writing my half reaction? No, right? So I need to write the entire oxalate ion and the entire permanganate ion, right? I can't just yank out the atom that I'm interested in, right? I've got to include the whole ion. So if you just go straight from electron standpoint, right? Carbon in oxalate goes from +3 to +4. So that's a loss of 1 electron. But here's the thing. Is this balanced in terms of number of carbons? Got 2 carbons on this side, only got 1 on this side. So you want to balance everything that's not oxygen first. So how can I balance carbon? I'm not doing this in like a solvent that contains carbon. The only thing I am allowed to do is put a coefficient of 2. Now here's where students make their mistake. If there's a coefficient of 2 here, if 1 carbon loses 1 electron, then 2 carbons are going to lose 2 electrons. Okay? You got to change this from a 1 to a 2. Because think about it. If 1 carbon lost 1 electron, then 2 carbons are going to lose 2 electrons. So that's the trap. Yes? So you're just like distributing 2. Essentially. You can think of it like that. Yeah. Because we wrote this 1 electron just based on the oxidation number, not looking at how many. But when we realize, oh, okay, there are actually 2 carbons here doing the oxidizing or being oxidized, that's why I need the 2 here. Does that make sense? That's a really good question. So now I ask myself, do I need to add any H2Os? I've got 4 oxygens on this side, got 4 oxygens on this side, so do I need to add any H2Os to this one? No, I'm done with this one. Woohoo! Now let's look at the reduction side. So manganese went from +7 to +2. The only way you can do that is by gaining 5 electrons, right? You gain 5 electrons, but I've got the oxygen to deal with here, right? So how do I balance the oxygen? How many H2Os? 4, right. I need 4 H2Os because I've got 4 oxygens on this side and 0 oxygens on this side, so I need 4 H2O. And the subscript here is L. By the way, that's not AQ, that's L, so that's the solvent. But now I've got hydrogen as a product, but there's no hydrogen as a reactant. So how many, well, what should I do to fix that? H plus, right. Because this is occurring in an acid solution, I can grab as many of these H pluses as I want from the solvent. And again, I'm being lazy with my subscripts here just to make it fit, right? That would be AQ, 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 that would be L. Because H plus is part of the solvent, since this is occurring in an acid solution, I can pull as many of those H pluses out of that solvent and throw them in my reaction as I want. Now, is this a balanced half reaction? It is, right? It is. I've got, how did I get from +7 to +2? Well, that's where the 5E minus comes from. I've got 4 oxygens and 4 oxygens. I've got 8 hydrogens and 8 hydrogens. So now I'm ready to add them up, right? Now I can add them up. So I look, I've got 2 and I've got 5, right? 5 isn't a multiple of 2. So I have to multiply them both by each other, right, to turn them both into 10, since 5 isn't a multiple of 2. So I multiply the oxidation half reaction by 5 and the reduction half reaction by 2. Don't forget to do it to everybody. Okay, a lot of students will just multiply the number of electrons by that coefficient. You got to multiply the entire thing by that coefficient. And now when I add them up, I am left with my final answer. Again, the order doesn't matter. If you wrote oxalate first, and then H plus, and then permanganate, right? Order is irrelevant. So long as you've got the correct substances on the correct side of the equation. 1 plus 3 plus 6 is no different than 6 plus 1 plus 1. Or 6, well, what did I say? I already forgot my 3 numbers. 1, 3, 6, 6, 3, 1, right? Order doesn't matter. How do we feel on this one? Ready to try another one? Again, I was lazy on my subscripts here to try to fit it all on the slide, and I still ran out of room. So if you run out of room, just make sure that I can find it. AQ, 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 H2O is liquid, and then that would be gas. All right, why don't we try this one? You give this one a try. Again, these are all in acid solution. Oops, wrong button. See what you came up with. So, do we agree on the oxidation numbers? Lead is being reduced, and the nitrogen is being oxidized. The lead in the oxide and the nitrogen in ammonia are the two substances of interest. This H2O is just thrown in there for fun, right? It's not part of the chemistry here, as this is written at least. Do we agree? So nitrogen lost 3 electrons. How do you get from -3 to 0? All right, you lose 3 electrons. But what do I need to deal with before I start balancing hydrogens? What do I need to deal with first? I got to balance the nitrogens before I can start dealing with hydrogens, right? You always deal with the non-oxygen and hydrogen substances first. I've got 2 nitrogens on this side. I've only got 1 nitrogen on this side. Nitrogen's not part of my solvent in any way. So what's the only way that I can balance nitrogen? Coefficient of 2, right? If 1 nitrogen would lose 3 electrons, then 2 nitrogens will lose 6. Got to make that change to your number of electrons, right? Because when we originally went through and assigned our oxidation numbers, we were just doing it based on, okay, this is +3, this is +1, and there are 3 of them, so this must be -3, right? We weren't looking at the quantity. But when we start balancing the half reaction, we have to look at quantity. So if if one nitrogen's losing 6, then one nitrogen's losing 2, then, excuse me, if one nitrogen is losing 3, then 2 nitrogens will lose 6. Does everyone see why we put the coefficient of 2 here in the first place? So I have 2 nitrogens here, I only got 1 over here. Got to balance for atoms as well as electrons. Now what do I do to address the hydrogen situation? You got to add 6H plus, right? And then the subscript here will be AQ. Left that off. That's AQ. Now are we good in terms of atoms and in terms of electrons? Yes, right? Now we're good. So we can move on to reduction. So lead goes from +2 to 0. What's the only way you can do that? By gaining 2 electrons. But I've got oxygen to contend with, which is why I added H2O. But now once I add H2O, I've got hydrogen I got to take care of. So that's why I added the 2H plus on the other side. Again, subscript here is L, subscript here is AQ. Do we agree on this one? Any questions on this reduction half reaction? How it came into being? So now we're ready to add. Right, I've got a coefficient of 6 here and a coefficient of 2 here. Well, that's nice because 6 is a multiple of 2. Right, so if I just multiply the entire reduction half reaction by 3, 3 times 2 is 6, and then those will cancel out. I don't have to do anything here. Oh, there's a random parenthesis. So when I add them up, look what also happens. Do any cleaning up you can. Right? 6H plus and 6H plus cancels out. So if you have other stuff that happens to cancel out, go ahead and cancel it out too. Clean it up as much as you can. These 2 H pluses just happen to cancel out. Right? So if stuff happens to cancel, great. Clean it up as much as you're able to. Gives us our final answer. Subscripted L for liquid. Did you get it right? You made a mistake. Do you see where you made it? Okay, try this one. I'll pause the recording. Again, this is all occurring in acid solution. We'll deal with bases on Monday. All right, let's go over this one. Involving the dichromate ion and 3 monatomic ions. So assigning oxidation numbers should go pretty quickly. The chromium in dichromate's what's being reduced, and the iron 2 is what's being oxidized. So for the half reaction for oxidation, that's really easy to deal with. No coefficients. We don't have to multiply by anything. We don't have to deal with any oxygens. We don't have to deal with any hydrogens. That's just straight up easy as it gets. But for the reduction, we do have to deal with a coefficient, right? The coefficient, essentially, I've got 2 chromiums on this side, 1 chromium on this side. If 1 chromium is gaining 3 electrons, what happens when there are 2 chromiums? I gain 6 electrons, right? Because the only way that I can balance chromium is by putting a coefficient of 2. So if 1 chromium gains 3, then 2 chromiums gain 6. Do we agree here? And then how do we deal with the oxygen? Well, we've got 7 oxygens, so we need 7 H2O, and that puts us in a problem because we have to deal with the hydrogen now, so we put 14 H plus on this side. So now we've got a reduction half reaction that's ready to add. Right? So we multiply the top one by 6, because coefficient here is 1, coefficient here is 6, so that's an easy transition to make. And then add, and we get our final answer. Did you get it right? Made a mistake? Do you see where you made it? I think we've got time for one more. Balance this one. Pause the recording. Okay, last problem of the day. Let's balance this redox. First, we have to assign our oxidation numbers. We see that copper metal becomes copper 2, so that's oxidation. And the nitrogen in nitrate becomes reduced. Right? Do we agree? So let's split this up into our half reactions. For the copper half reaction, that's really easy. I don't have to deal with any oxygens or hydrogens or anything like that, right? I don't have to deal with any coefficients either. It's 1 to 1, so it's literally just adding the 2 electrons on there. For the reduction half reaction, I do have to deal with oxygen, because I've got more oxygen on the product side than I do on the reactant side. So I need to add H2O to the product side, which means I need to add H plus to the reactant side. So do we agree on the 2 half reactions? So now I'm ready to add coefficient of 2 here, coefficient of 1 here. So I'm going to multiply the entire reduction half reaction by 2, and then do my adding, giving me my final answer. Did you get it right? Good deal. All right, so remember, on Monday when we talk about balancing in basic solution, we're going to take what we learned today and literally just add one more step to it. So if today didn't make sense, please review over the weekend. And then on Monday, we'll talk about balancing in basic solution. Have a good week.